finishing up process I think I promised you wouldn't like, so here goes. This is the last question from section 16. So we're going to be finding the exact value of y equals x cubed from x equals 0 to x equals 1. So I'm having a little bit technical issues, so that's why I'm kind of hesitating and pausing. So I'm going to mute you all because I was getting some weird feedback as well. Okay, so hopefully right now you are looking at the paper, right? Here is the curve y equals x cubed from x equals 0 to x equals 1. They ask you to use a property that 1 cubed plus 2 cubed plus 3 cubed is equal to this guy, and we shall do that. And it's basically it's broken into two parts. The first part is that we are going to take this fella here, and I'll put a box around the bit that is the answer to A when we get to it. And then in part B, and we use this information, and we're actually going to find what the area of that is. I'm just going to do a little bit more than they're asking for, because I think it's worth it. So since I'm a kind of visual person, if you do y equals x cubed, it essentially looks like that. I know it goes down here, but we're only interested in from 0 to 1. And we already looked at this last time. If you look at the Riemann sum Rn, the limit as n tends to infinity of Rn, this Riemann sum, will give us the area, the exact area under that curve. So I need to find delta x. And delta x is b take away a over n. And in this story, at least I know who a and b is as numbers. B is 1 and A is 0, and N is just N. So that guy becomes 1 over N. I also need to find out what's going to go here, A plus this guy. So A plus delta xi becomes 0 plus that guy times I, and that just becomes I over N. And now I need to find out what the value of this function is, which just becomes the value of the function at I over N. And since the function is x cubed, this becomes I over N cubed. And you might well watch this video again. And say, okay, where did that come from? Where did this come from? But right now, I have all the pieces that need to fit in here. The limit as n tends to infinity of sigma I equals 1 to n delta x function. And the function is I over n cubed, and delta x is 1 over n. And that guy is the answer for A. So if I could find out what this is equal to when n goes to infinity, what I'm essentially doing is breaking this shape into an infinite number of very tiny strips. Can you imagine if you made the strips, if you made enough strips, wouldn't you get a really accurate answer to the area under the curve? And if you could do an infinite number, theoretically at least, you'd get the exact area. So that's A done. Finito. You then go on in part B and get us to find what the answer to this is. So when I come to part B, I am going to put a fraction in here that represents this entire area. So this is the working that's going to get that answer. It's going to be the limit as n tends to infinity of I equals 1 to n, 1 over n, I over n cubed. I'll try and take each step that I do slowly. 1 over n times I cubed over n cubed. If you take I over n and you cube it, don't you get the top guy and bottom guy cubed? That's essentially what that is. In this next line, I'm going to combine these two together to get 1 over n4 times an I cubed. I don't know if you need brackets, but I guess I'll put some brackets around it. There we go. Now, I could have called it I cubed over n to the 4. I mean, I could have done that. That would have been correct as well. Now, what's next? Well, they tell me in the notes, in the question, that I can replace this guy here by that. So this I cubed can be replaced by an n plus 1 all over 2 squared. And the reason I wrote it this way is because I think it's a little bit easier to see what's going on when you separate it. Oh, and I almost forgot. That disappears when you do it. So all of this just becomes that. So according to the notes, you can replace the sigma I cubed by this. So the sigma disappears, the I cubed disappears, and you get this guy times this guy instead. So now we have the limit as n tends to infinity. 1 over n to the 4. If you square each term, you get that. If you FOIL this top guy out, and if you combine the bottom two guys together, you get that. I am getting really close to the finish here. If I can find out what the limit of this fraction is when n goes to infinity, the answer to that is the area under the curve. That's the number that's going to go here. Now, way back in Calc 1, can you remember doing limits of things as x went to infinity and x went to 1 and n and k and all the other letters? Remember doing those, guys? So I'm going to use that technique. There are actually two different ways to do this. Both of them work. Can you remember the trick where you divided the top and bottom by n to the power of 4? Does that ring any bells for you? Where you take a fraction and you divide the top and bottom. And that's the one I'm going to choose. So I'm going to divide everybody in the top by n to the 4 and everybody on the bottom by n to the 4. And we now have the limit as n tends to infinity of 1, 2 over n, and 1 over n squared, all over 4. So this limit is equivalent to that limit. And then you just plug n as infinite and see what gets. Right. What will 2 over infinity get you? What's 2 over infinity worth?
0.
And isn't 1 over infinity squared also 0? So don't you just get 1 plus 0 on the top and 4 on the bottom? And after all that hard work, the answer that goes in here is a quarter. And that's the question finished. Would you agree you do not want... Yes.
Ways? I'm
yeah.
sorry.
The other way,
two different ways.
Yeah. The other way is using a guy called L'Hopital. Can you remember L'Hopital, where you differentiated the top and you differentiated the bottom? That was the second
French guy?
method. Yeah. I think he was Belgian, but
Bertulli's guy?
French. Le Hospital guy. Le Hospital. Him.
La Hospital?
Yes. That's who I'm calling him. Right. For those who want to see the second method, here is the original ugly guy that we were trying to find the limit of. And if you use Le Hospital or Le Hopital, I think his correct pronunciation is, you put a little L there to tell people that's what you're doing. And according to the theory, you differentiate the top and the bottom separately. So this guy gets you 4n cubed, this guy gets you 6n squared, this guy gets you 2n, and this guy in the bottom gets you 8n. And if it doesn't work, then you just do Le Hopital again until it does work. So if I do the top and differentiate it again, I get that. And if I do the bottom is 4. My apologies. The bottom is 4. And if you do Le Hopital again, and if you do Le Hopital one more time, which better be a quarter. And if it's not, it's because I can't count. Actually, it's probably 96. So it is a quarter. I wouldn't have done Le Hopital. Isn't dividing top and bottom by n to the 4 a lot quicker. But there was 2 techniques. Both of which give you the same answer, that it is a quarter. I would not choose to do this technique to find the exact area under a curve. Can you imagine how much work would be involved? Every single question. And that's why you're only going to see it once. And we're going to lead you to another place where we can get the same answer without having to do all this. A really clean way of doing it. So, as far as you're concerned, these are the 2 things that fit in the boxes in question 16. What I've done here is how I got those numbers, but these are the answers. And you will not be given a test question or a final exam question using that technique, right? We're showing it so that it isn't, so that you've experienced it, but nothing that I would expect you to be examined on. I guess that's good news, right? So what's next? Oh, before I move on, is there anything more that you want to talk about in that question? It's probably something you're going to go back and look at the video and say, okay, how did he do from line 3 to line 4? Then what did he do to get line 5? It's something you just have to pause and, let it sink in. So I wouldn't be too worried if that happens to be your situation. Right, what I'm doing now is setting things up for our next section. And that is section 5.2. It's called the definite integral. Now, if you have a function and you want to find the area under its curve, like this guy here, and it starts at A and it finishes at B, what we call the area under the curve is this. This is described in notation as that. So the area under the curve between x equals A and x equals B of the function f of x, and the dx is just part of that notation. So this is integral notation. This is actually how almost every integral area under curve is written. It's a much more concise way of doing it. So for instance, if I went and said to you, I'm looking for that. Looking at that, can you see that you're looking at the curve y equals x squared? You're starting at 1 and you're finishing at 2. So what you're being asked to find here is that area under the curve. So do you see that's a very concise way of describing the question? Right? Instead of using a lot of English, find the area under the curve y equals x squared from x equals 1 to x equals 2, which is how you'd have to write it in English. Can't we just write it down in this nice, concise notation? This is called the definite integral. We go. So I would like to find these guys, but I don't want to spend half an hour doing that. Agreed? Don't we want to find other ways, better, easier ways to find areas under curves? And that's what this section is going to do. It is going to show you some tricks of the trade for getting exact values for the area under the curve and not doing it numerically with the Simpsons or trapezoid rule, and not doing it that horrible 20 lines of algebra way, but by doing it by other means. So here is a version of one of these questions. We are trying to find the area under this curve. Here's another example. Actually, I might do this one first. Now, there is a little idiosyncrasy that I might as well get over with right now. If the area of the curve is above the x-axis, then this answer is positive. But if the thing is below the x-axis, the area will be a negative number. Now, I know we normally say, look, you can't get negative areas, but can I break that rule now? You are allowed negative areas in integration. All that it means is that the curve is below the x-axis. Positive means it's above. Does that kind of make sense, that you might get a difference between the two situations? Right. Now, if that is possible, couldn't you get a situation like this? That if I did the area between 0 and 2 pi, couldn't the area actually end up being 0? Couldn't this fellow up here be positive 3 and this guy here be negative 3? So when you put them together, don't they cancel each other out? The reason for that is that the area that we're talking about isn't a physical area. It's essentially, it's called a net area. Net area is positive, net area is negative, the net area is 0. So, suppose I wanted, again, to find this fella. Let's see what the questions are asking us to do. The first one wants us to get the area under the curve from 0 to 4. Well, you do not need to do anything except realize that aren't you just asked to find this area here? And can't we use geometry to do that? I mean, if I wanted to find the area of this shape, me personally, I'd probably split it into a triangle and a rectangle. Would that seem a reasonable way to split it? And then just find the area and add them together. So if you look at the triangle, it's half base times height. The scale that they're using here is something that you have to be aware of. So it's 1/2 a base of 4 times a height of 4. And then the rectangle is 4 by 2. And so that's going to get me 8. And that bit's going to get me 8. So that area would be 16. Are we okay with what I've just done there? How I found the area under the curve by simply just realizing that it's a shape that I can get the area of using just geometry. Now, suppose you wanted to do the next one, the area from 0 to 10. By the way, there's 10. Maybe I should do a clean picture of that. If you wanted to do 0 to 10, couldn't you split the picture? Oh, there's lots of different ways to split it. But couldn't I split it up into 4 pieces? Maybe those 4? Couple of triangles, couple of rectangles. I mean, you could split it up different ways, right? I'm not saying that's the only way to do it. Haven't we already done these 2 guys? Wasn't that 16? So I can use that answer. And then don't I just need to add this guy and this guy? So these 2 add up to 16. This fella from here to here is 2 times 6. And this triangle is 4 by 6. So that's 1/2, 4 times 6. What does that get me? That gets me 16, add 12, add 12. And I believe the answer is 40. Any questions about that, or does this seem relatively straightforward? Couldn't I ask you to get the area from 4 to 8? Get the area from 2 to 6? Can you pick any start number and any finish number, and then just look at the piece of the picture and break it up into triangles and rectangles, right? And get the area that way. Now, all of these guys right now are above the axis. That is why this answer is positive. The next one says 10 to 14. Now, 10 to 14 is this piece here. Right? Starting at 10 and finishing at 14. Now, the good news is it's one rectangle, right? One triangle. And its base is 4 units, so it's 1/2 of 4. Using the fact that the scale here is 2, 4, and 6, that makes it 6. But the answer is not 12. Not quite 12. What would this dotted integral area be?
-12?
Exactly. So will you make sure that if you're doing areas that are under curves and only under the curve, that you do negatives, right? And if it's only above, then the areas are positive, right? It's just a little thing you have to be careful of, right? Because we're really talking net area here, not physical area. And so there is a subtle difference, isn't there? You can have negative numbers with net areas, right? That is allowed. Now, if you go to the final question, which says you start at 0 and you finish at, where would 18 be? 18, you'd finish here. Well, wouldn't it be all of this guy and these pieces? So what do I already know? Well, I know that from here to here, because I've already done that, is positive 40. And don't I know this little piece, because I've already done it, is negative 12. So I can save myself some work by just using those answers, which means the only guy that I've left to get is this little piece at the end, right? It's the only one I haven't already calculated. I would probably split it like that. And that's going to be 4 times 4. And a little triangle, 1/2 of 4 times 2. Have you noticed that I put the negatives here to represent that these are negative net areas? So what have I got? I have a 40, take away a 12, take away a 16, take away a 4. So 16, 20, 32, away from that, the net area is 8. So we are finding areas under curves, exact values, and we're not doing, you know, the strips in Simpson's rule, and we're not doing that horrible algebra. We're just taking the shape and breaking it into triangles and rectangles and doing it essentially using geometry, but remembering that above the axis is positive net area and below the axis is a negative net area. Any questions about that, or does that actually seem a lot easier and quicker than and less laborious than what we've done in the past?
Yeah, it looked kind of complicated at first, but once you just start breaking it down, it immediately became easier.
Right. So you just have to know how to cut the thing up. Think of it as like a cake. And I decided to cut this shape up in the way I did it. You might have looked at it from a different viewpoint. You're still going to get the right answer, right? You might cut the triangle in a different way than me, or the rectangle and the triangle in a different way than me. And so that is the first one of that kind. Here's another one. A little bit different, but not a lot. The way I see this, do you see a triangle, half a circle, triangle? You agree? I would probably put in some more scales because it's hard to tell when you only see a couple of numbers. So it looks to me like the boxes horizontally are in, each one's worth 3. And going vertically, each one is also worth 3. Okay. Let's go for the whole one. I'm not going to do these two. I'm going to go for the whole area, starting at 0 and finishing at 21. Then won't we have a triangle over here? At the end, another little baby triangle. Won't those both be positive things? And then right in the middle, half a circle, right? So let's put the package together. This triangle is a half of a base of 6 times a height of 12. And the little baby triangle at the end is a half of 3 times 3. Now the guy in the middle is below, so if I stick the negative there, I've taken care of that. How am I going to find the exact area of this half circle?
Pi r squared over 2.
Yeah, half of a whole circle. Pi r squared over 2. A half of pi times, oh, there's a good question. There's a little dot to help you. What's the radius of this circle? If it was a complete circle, what would its radius be?
6.
Agreed. How did you get it? What direction did you use? Or how did you get it? You can tell me.
Half of the diameter.
Okay, you went from there to there is 12, so it's 6. My brain was working differently, but that doesn't mean I'm better or worse than you. It just means I'm different. Isn't that distance 6? And that's also a radius. That's just how my brain works. But it's a 6. So it's a half of 6 squared, which is 18 pi. Now this guy gets you 3 times 12, which is 36. And this guy is a bit messy, he gets you 9/4. And this guy in the middle is him. I have to turn him into quarters, which is 120, 144. Add 5 is 153 quarters. Take away 18 pi. It's not the prettiest answer in the world, but we're not being asked to find a pretty answer. We're only being asked to find the exact answer, which means you sometimes have to leave things in quite ugly form, right? Which you get, it's not very pretty, but it's the answer. Again, I'll pause for a minute. Are we comfortable if you are given a shape that a drawing like this, that you could find various integrals by basically just, using geometry, right? Rectangles, triangles, and bits of circles. That's probably the only shapes you really know how to get areas of, isn't it? Triangles, rectangles, and half a circles. So that's all they're ever going to ask you, those shapes. Any questions before I move on? Are we good? Okay, let's move on then. What I'm going to kind of do now is a very short section, this, which is nice, I think. So you should be looking at 7 questions compared to what we've done. Some sections are really long, some are very fast. Can you see that's a similar version to the one that we did earlier? Number schemes will differ. Each question's a little bit different. There's a version of the half circle one. Again, the numbers will be different. You know, the way WebAssign does things is it randomly generates different versions of the same question. So your homework questions probably won't be the exact same ones as I just showed you, but they will look very similar to the ones I showed you, right? Then the height might be 10, not 5, you know, things like that. Now, we don't want that. Well, you might want that, but that's the solution. I want to do the solution with you. Yay, good. Okay. I'm going to do a version of question 3. And again, it's find the exact area. And it looks like this. In this question, it's going to be the exact area from x is -7 to x is 4 of 1 minus x dx. And the one I'm going to do is the integral from -1 to 3 of 2x plus 1, because I want to. So I'm just showing you the method that you would use to do a question like question 3. Okay. So let's close that off. And right, there's the question. Has anybody got any idea how I'm going to approach getting the exact value using geometry? Anybody get any ideas what I show you?
Well, you know it's going to be a straight line because it's just 2x plus 1. And then, so you could draw it out
Agreed.
and then go from -1 to 3 and then just do the same thing we were doing before.
You nailed it.
Just
That's
make it like
exactly
a
what I'm going to do. Yep. Exactly what I'm going to do. So I'm going to start at -1, finish at 3. I don't even need to be, you know, it's better on square paper because I can count boxes, but, you know, I don't need to be perfect. I'm sure I can figure out. Right. Imagine the line with this equation. Now at x equals -1, it's -1. At x equals 0, it's 1. And can you imagine it going something like that, right? Oh God, that was a bad sketch. Can I redo my sketch again now that I've started it? Because if I do my sketch accurately, I guess I can get away with it, right? It's huge. But I think I should do a little bit nicer version. So if you can bear with me, I'm just going to change my scale a little bit. So there we go. So -1, 0, 1, 2, 3. And at x equals -1, the y coordinate, 2 lots in, is -1, so that guy is good. And when x equals 0, the y coordinate is 1, which is there. There, I'm much happier now. Yeah. Now, can you imagine square paper? I could probably do a much better job, but essentially everything you need to know is here. I guess I could find out what the value is at 3. When you plug in 3, this guy up here should be 7, right? Now, when I look at what is the area under this fella, it's basically 2 triangles. I know it looks like it's 1, but isn't there a little baby one on the left and a huge honking big one on the right? And so if I want to get the area under it, shouldn't I find these two and then combine them? Right, the little baby one, that guy there, by the way, is -1/2, is half the base, which is which is 1/2, and the height, which is 1. So that's 1/4. But because it's below the axis, it's -1/4. And then the other big chunk, call that guy B, this guy here, he's also a triangle. And what's he? He's 1/2 of 3.5 times 7. And so what's that? 49 quarters. And so the net area from -3 to 1 of this guy is basically that little piece that's negative with this big piece. And you stick them together and it comes out as a rather interesting answer. It comes out as a nice answer. It's 12. So can you imagine that you could use this technique for any straight line, right? The integral from 0 to 2 of 5x plus 1, right? Those kind of things. Draw the thing, find out where the x-intercept is, because you'll need that, because that separates the guy below from the guy above. And if you're wondering where the -1/2 came from, I solved when is this 0, and that told me it was -1/2. Are we okay with that guy?
Is it okay if you scoot your
You
paper
only, I
up
think
a
you
little
only,
bit? Sorry.
Sure. No, I don't
Thank
know what
you.
the camera sees. Right.
Oh, yeah.
But are you okay? Right. So you're only going to get one straight line. I think the straight line that you get is something like 1 minus x. So that's a pretty easy line going down the way. I hope. I'll move this guy over here. And we'll show you the last bit. Suppose I wanted to find the integral from a to b of some function f of x. Right, so that's the area under the curve from a to b. Right. And we're being asked to find this, not exactly directly, but to take some integrals and combine them together. So I've got this fella, and I've got this fella. What would they combine to be as a single integral? Because that's what they're wanting. So the area under the curve from -3 to 3, and the area under the curve from 3 to 5. What was the single integral that would represent that same thing be? Where would we begin? What value of x?
-3 to 5.
And we have just answered the question. Now, this is a bit weird, but it's true. If you calculate the area under a curve from a big number to a small number, in other words, you go in the wrong direction, it's the same answer as doing it the usual way, but negative. And so you're just going to trust me that that's just what it is, right? So suppose I gave you the integral from 0 to 2, and then it went from 2 to 6. And then it had take away that guy. That guy is back to front and upside down, isn't he? Isn't the integral from 10 to 6 the same thing as the negative the integral from 6 to 10? And then if you stick another negative on it, doesn't that simply just become that fella? Now, do those all match nicely? Right? Boom, boom, boom. Yep. And they start at 0 and they finish at 10. And that would be the answer that you're looking for. Let me do a different negative one. Suppose I did integral from 1 to 10. And then I subtract the integral from 1 to 7. Now, these integrals are actually the right order. So there's nothing I'm going to be able to do that's going to help this one. And I don't want you to think of what we did here. I want you to think of cutting bits out of things. So the area under the curve from 1 to 10 has the bit from 1 to 7 cut away from it, right? Taken away from it. What single integral would that represent now?
Would
1 to
that
10.
turn into
Cut.
7 to 10?
It would exactly turn into that, yes. So if you like, what we're learning here, just for a little while, is the algebra of integrals. In other words, what you can do with them, which isn't really a lot. Can't you just add and subtract them in different ways? You can add things together and make a single integral. You can subtract things and make them single integrals. Or you can switch the order and then combine them and again make single integrals. Are we good? Right, one last thing and we're done. That means this section is done. Suppose I tell you the integral from 1 to 3 of f of x. Suppose somehow or other I found out the answer was 10. And from 1 to 3 of a different function g of x, and I found out that this answer was 15. I should be able to figure out these three things. Right, now, you've never seen these probably in your life before, but let's see if we can intuitively think what it might be. If this guy is worth 10 and this guy is worth 15, what do you think you would get if you added the functions together and found the area under that combined function? What would be a sensible answer? If this was 10 and this was 15, what would you get if you joined them together?
25.
Yeah, wouldn't you just get the first guy plus the second guy? 25. Does that make sense? Right. What happens if you subtract them? Well, wouldn't you get the first guy, take away the second guy, in this case, the net area? Remember, net area is allowed to have negative numbers, would be -5. And the final question for today. What do you think this horrible mess would be?
Just those numbers, but times 2 and 4 respectively, and added together.
Yeah. So as long as you know the building blocks of integrals, can't you combine them, add them, subtract them? 2 of one, take away 4 of the other, whatever it happens to be, by simply just using these numbers and doing the same calculation, right? 3 of these, take away 2 of them. 3 of these, take away 2 of them then. This guy plus that guy, okay, this answer plus that answer. Right? It's a very one-for-one kind of relationship, isn't it? And that's pretty good because we've now finished the section. They're not all going to be as quick as this one, but isn't it nice that we got at least one quick one? Right, everybody say hi for attendance, and I shall see you all tomorrow, where I will tell you about the fundamental theorem of calculus, part 1 and part 2, which is basically antiderivatives. Bye-bye then. They are. I like them. I think compared to how you had to do it before, these are going to be so much smoother, right? No
Certainly
more,
hope so.
no more
Thank you.
20 strips, no more 12 lines of algebra, or not even cutting it up into triangles and adding them up. Pure algebra. So much quicker.
That sounds nice.
It does. I like it. It's going to
Thank
be
you
good.
for class.
You
Thank
are
you.
welcome, Brendan.
you.
Bye-bye. Right, anybody got a question? Of course, as always, just hang about in the end. If not, I'll see you tomorrow.
See you tomorrow.
Bye-bye.
Bye-bye.
Bye-bye, Besida.
Will you be at office hours tomorrow?
Should be. Is there something you want right now?
Yeah, I was just wondering because
Sure.
I'm gonna try to finish as much homework tonight, but if I had any questions. And that would
Oh,
be
okay.
at 10 a.m.
Sure. Yes. It might be a little bit after 10, and the only reason for that is that I have a class at 9, and I just get those people to do the office hour by just waiting behind. So I may start
Yeah.
at 10 past, but I will start. Okay?
Okay.
But if there's a question right now I can help you with, I can do that.
Yeah, I actually did have a question. I know you covered it briefly in class, and it's going back to which one was it? Sorry.
That's fine. It's probably 5-1 or 7-7. 5-1 was left to right and all that stuff, and 7-7 is Simpsons and trapezoidal.
Yeah, it was 5-1 question 2 where the x values are not at regular intervals.
Gotcha.
Yeah, just how would I?
Right.
Yeah, how would I calculate?
Let me show you that. Right. Let me put that picture up so we can see what I'm talking about. So you're basically talking about this question here, right? So what you're going to do here is you're going to imagine, I mean, you could plot it and draw it if you like, but I can get away with that. The first strip it goes from 0 to 10. So it's 10 units wide and it's 180 high. The next strip is going to only be 5 units wide because from 10 to 15 is 5 units. And its height will be the big number, 319. Well, you might say, why am I choosing the big number and not the little number? Upper estimate. See that?
Yeah.
Upper approximation. So you're going to go 10 times 180, 5 times 319, 5 times 442. The next one from here to here, won't that be 12 times 742, right? The bigger number. The next one is 27 times 1100. The next one is tiny, it's just 3 times 1430. And the last one is going to be 63 times 4052. So does that make sense that you're not doing a normal equally width strip? Each strip depends on the start and finish number in your table.